Good evening once again. We're on to further mathematics, but today we're considering pure mathematics. And one of those topics we're going to see in pure mathematics is the matter of what? Trigonometric ratios and identity. Sometime along the line, we're going to have these ideas play into vectors and mechanics and statistics and probability. But for now, we'll just treat it as pure math and see how it flows. So, what is trigonometry? It's not a concept you're new to, because in our mathematics, we are treated trigonometry as a branch of geometry. When I tried to talk about the geometry experience, I talked about geometry in terms of 4 crucial areas. I hope I'm right with that. I talked about geometry in the matter of what is called formal geometry, deductive reasoning to show how shapes are related in terms of angles. Now, we also have what is called mensuration. Mensuration, having to do with solid shapes, plane shapes, and talking about perimeter, area, and volume essentially. I also talked about the matter of construction and loci, that is showing relevant theorems in or showing relevant behavior of theorems, secular or plane theorems, by carrying out constructions. We'll carry out constructions using a ruler, a pencil, a compass, and the likes, protractor, as the case may be sometimes. What we obtain is more based on what we have drawn out. So that's construction and loci. Now, there's also another aspect that talks about what? Trigonometry. Trigonometry essentially talks about the behavior of a triangle. Sorry about that. Okay, I was talking about trigonometry, and the word trigonometry essentially means triangle measurement. So the building block for trigonometry is the right angle triangle. The building block for trigonometry is what is called the right angle triangle. So, and when we mention trigonometry, 2 major ideas come to mind, or we can say 3. We have the matter of what is called trigonometric ratios, which will give rise to what is called trigonometric identities. And also, we have what is called your Pythagoras theorem. Some books will say Pythagoras theorem or Pythagoras rule. So these 3 ideas are essential to our understanding of trigonometric ratios. To understanding of trigonometry, trigonometric ratios, trigonometric identities, and Pythagoras theorem. All right, so we've talked about trigonometric ratios, trigonometric identities, and Pythagoras theorem. These 2 will help us furnish us with this one, or we'll furnish this particular one. But these are the 3 essential ideas we'll be talking about. We'll talk about trigonometric, we're talking about trigonometry. There's also other aspects that boils down to things like what you call cosine rule, sine rule, but we wouldn't go much into those ones now. We'll just focus on those ones that will help us in our further math experience. Now, the next important idea we must take note of when we have a right angle triangle is to identify what is called the opposites. The opposite, the adjacent, and essentially the hypotenuse. Opposite, adjacent, and hypotenuse, because these 3 ideas will help us build what is called our trigonometric ratios. We know from our basic understanding of arithmetic that a ratio is relating 2 sides or relating 2 quantities that are the same. So when we say trigonometric ratio, it means the measurement of an angle with respect to what? 2 defined sides. So Now, I will call this angle X, for instance. If I call this angle X, the side this angle sees is called the opposite. And the side that this angle is sitting on is called the adjacent. To further confuse you further, let me flip this angle upside down and show you something that is happening. Now, in this iteration, I'll put the angle X here. What I've done is just to turn it. Where the angle is seen will be called the opposite. Where the angle is hanging on is called the adjacent. So it's important you get these ideas very clear in developing this concept. Here, the angle, the side, the angle sits on the adjacent. Here, the angle hangs on the adjacent. The opposite is always the angle. The opposite is always the side the angle is seen. The opposite is the side the angle is seen. Now, this is what we call the hypotenuse. The hypotenuse is where 90 degrees is seen. Whatever 90 degrees is seen is called the hypotenuse. All right. So, by way of continuing my work, I'm going to clean this part of the board and try to expatiate on this idea. Now, let's assume I draw this and I change the direction this way, and I bring the angle X this way. This is where the angle will be seen, and this will now be called the opposite. So you see that in this direction now, the angle looks downwards. And where this 90 degrees is seen is called the hypotenuse. And this angle will be resting on this side. It's now called the adjacent. So it's important for you to understand what's happening here, because every other thing we're going to be doing will be dependent on how well you've understood this concept. So by way of still trying to confuse you, let me now flip it this way. If this is the angle in question and this 90 degrees, what 90 degrees sees is called the hypotenuse. What this angle is seeing is called the what? It's called the opposite. Okay, let's take a different, I want to see if I could take a different feel to it. Okay, it doesn't really matter. It's called the opposite. And what this angle is resting on, is resting on this side, is called the adjacent. So you see that these are the labelings we have for this diagram. I mean, it's important you take note of them, because these are the things we're going to now use to develop what is called trigonometric ratios. All right, so I'll clean this off and we'll start off the next concept. So let's start by looking at trigonometric ratios. Now, what is a trigonometric ratio? Essentially, a trigonometric ratio expresses the ratio of two sides of a right angle triangle. A trigonometric ratio will express the ratio of what? Two sides of a right angle triangle. So let's look at the possibilities we can have. We have opposite, adjacent, and hypotenuse. So we can have ratios that, so I'm going to use this because sometimes when we talk of trigonometric ratios, students seem to see it as one abstract thing. So I've used O for opposite, A for adjacent, and H for hypotenuse. Let me now show you how this can stretch into the concept you'll see later in further maths called permutation and combination. What are the possible number of occurrences you can have? Now, let's look at this. You can have O with A, you can have O with H, you can have A with H. I see that. Now, you can also flip this to become A with O, H with O, and what? H with A. This iteration already suggests to me that there are 6 types of trigonometric ratios. Now, with the way I've done it, it means this will be what? Ratio would normally talk about what? Numerator over denominator. So a ratio will usually express the numerator over the denominator. So with what you've seen, there are 6 possible outcomes when we talk about what? Ratios. Now, numerator over denominator, 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 numerator over denominator. So let me give you all the types and show you what is going to happen. From your secondary school, early secondary school, there's something you were taught. As a student of mathematics, you are expected to remember these 3 basic types of ratios. This S stands for sine, this one stands for cosine, and this stands for what? Tangent. Sine, cosine, and what? Tangent. Remember that the ratio expresses the relationship. And in this context, our trigonometric ratios will express the ratio of 2 known sides of a right angle triangle, usually the reference triangle used to explain this model. All right. So we look at this. Sine is this, cosine is this, adjacent is this. Now, for me, I usually choose to write it this way. I write O over H, A over H, and this is what? O over A, where O stands for opposite, A stands for adjacent, and H will stand for what? Hypotenuse. All right, so with that settled, these are the basic ones you have, but you discover that I also have another 3. I say that. So if this is O over A, if I flip it, what I'm going to get is what is called the cotangent. And how do I express the cotangent? I will express cotangent as what? A over O. I'm just handling it as if I've never done trigonometry. I've never done trigonometry before, because if you have done permutation, you discover that the number of possible outcomes there would have been 6. But that's an Easter egg for a topic you will see later. But just to help you see that sometimes you must understand that when it comes to this matter of mathematics, the ideas are connected. Your task is to try to see this connection. Now, look at this one. Cosine will be seconds. Seconds. So this is the reciprocal of this. You know, because remember that when we're treating reciprocal, I told you that what reciprocal does essentially is to turn. So the reciprocal of this is what? Second. So it will turn this. I now have what? H over A. So second will be this. Now let's come to sine. The reciprocal of sine is called cosecant. And that will give me what? H over O. So this gives you the illustration of the 6 types of trigonometric ratios you have. In mathematics, we usually limit it to just 3, but in further mathematics, you must know that there are 6 types of what? Trigonometric ratios. All right, so I'll leave it at that because I'll also come back later to drive these ideas further, but this is more or less like a descriptive class to help you see in perspective what's happening in this realm. All right, so we're done with that. So I'm going to give you a summary. Let me give you something like a summary. We have sine. So we generally call it sine theta. Or like in this context, okay, let's draw the triangle first so that we have a reference to what we are doing. O, A, H. So we have what is called sine X. Sine X will be equal to what? O over H. Remember, this is 90 degrees. This 90 degrees is important because that's what tells us what to do. Now, we have what is called cosine or cos x. Short form for cosine is what? Cos. And that is called adjacent over hypotenuse. We have what is called tan x. And that is called opposite over what? Adjacent. Now, we come to the big one. Now, we have what is called cosec. Cosec x. And that will be equal to what? Hypotenuse over opposite, which is equal to 1 over sine x. We come to the next, which is called secant or sec x, which is hypotenuse over adjacent. And that is 1 over what? Cos x. We come to the last one, which is called cot. The short form of cotan is cot. Cot x, and that will be what? Adjacent over opposite. And that is 1 over tan x. So that is what we should know about trigonometric ratios. So pause there and then we'll take another ideas shortly. Okay, so close to the description on our trigonometric ratios will be a very important idea which we call the Pythagoras theorem. Pythagoras theorem is also narrated on the premise of what a right angle triangle is. It says that if I have the opposite sides known as what, let me say A, B, and the opposite side is C. Pythagoras said that C squared, that the hypotenuse side of a right angle triangle will be the square of it will be equal to squaring the other sides and adding them up. So if I square this side and I square this side and I add them up, I'm going to get this squared. So what that means invariably from our knowledge of change of subject of formula, it means that C squared, which is A squared plus B squared, will mean that C will be equal to the square root of what? A squared plus what? B squared. We can also make A the subject of the formula and some other things will happen. For instance, from here, I can say that A squared plus B squared is equal to C squared, meaning that A will be equal to C squared minus B squared, the square root. And by that implication, B will be equal to the square root of what? C squared minus A squared. This idea is very important. It's very, very important. So we've talked about trigonometric ratios. We talked about Pythagoras theorem. Now we're going to take problems and see how these two ideas are connected, because it's important to know how these ideas are connected. Okay, so we'll take some problems now. Remember, our official text for this work will be the new further maths project. This should be the, okay, they call it the revised and extended version. So this is what we'll be using for this course. So if you are following us online or you get to watch this video much later, it would be nice for you to have this textbook to have a flow on what we're doing. And for further maths, I always give this counsel. When you solve exercises in further mathematics, please leave no question behind. Yeah, leave no question behind. For mathematics, you can go away freely, but for further mathematics, when you start doing your revision, follow every example, follow every question, follow every exercise closely, because every exercise or example has an idea it would pass across to you, right? So we will take an example now, and that will be on page 156 of our text. It says, given that sine theta is equal to 5 over 13, and what theta is an acute angle. I didn't make mention of this, but maybe much later when I'm explaining, I will delve more into this concept of acute angle. Now, what's an acute angle? You may want to look up my videos in grade 10. I think that is formal geometry, points, lines, and angles. I did extensive work there on what types of angles we have and what an acute angle is. An acute angle essentially is any angle that is less than 90 degrees. Now, for a right angle triangle, one of the angles is 90 degrees. So the other two angles must be obtuse, must be acute. So the description here will be taking into consideration the context that what the angles described here are what acute, knowing fully well that one of the angles there is already what 90 degrees, because we know that the sum of the angles in a triangle is 180 degrees. So if one angle is 90, it means that the two other angles must sum up to what 90 degrees, and as such, each one of them must be obtuse, must be acute. Sorry about that, I'm always using the obtuse thing. All right, so with this, the first thing we want to do is to draw a right angle triangle. And then we just try to identify what theta is. We said that it's acute. So the acute will suggest that you must draw a right angle triangle. Now, what is sine? Sine is essentially opposite over hypotenuse. It means from this diagram that the hypotenuse is 13. And what is opposite? We said that the side opposite is the angle that is the side that the angle is same. Please pardon me if I've always played with this technical error. Please pardon me. The side the angle is same is called the opposite. So in this setup, the opposite will be 5. So we need to look for the adjacent. Let's call that A. How do we obtain the adjacent? We apply our knowledge of Pythagoras. So A, let's call this one letter A. A will now be equal to what? 13 squared minus 5 squared. Remember that Pythagoras said that this squared plus this squared will give me this. So if I'm going to get this one, it will be square this and now say minus what? Squaring of this. At this point, there are two ways you can go about this. I'll just use the approach that's quite simple for us. That'll be square root. Sorry about that. That'll be square root. And A will be equal to what? Square root of what? 144. And A will simply be 12. So this will be equal to 12. So we now know the sides. And now we are told to find what is cos theta. Cos theta we know to be what? Adjacent over hypotenuse. So what is adjacent now? 12. What is hypotenuse? 13. I seen it. It becomes very easy for us to solve the problem. Now we're told to find tan. What is tan theta? Opposite over adjacent. What is opposite? 5. The side the angle is same. What's adjacent? 12. I see how fast you now solve because you know what you have done. Next one says sec. What is sec theta? Sec. Anytime you see here the word sec, it means 1 over cosine. 1 over cosine. So when you see sec, it's the reciprocal of cosine. When you see cosec, it's the reciprocal of sine. It's like a crossbow thing. So this will be 1 over cos theta. What is cos theta? Cos theta is what? 13 over, rather 12 over 13. So sec theta will be what? Flip it. That'll be 13 over 12. Flip it, and that gives you your final answer. Now, the last one there talks about, okay, there's still one more, cosec theta. What is cosec theta? Cosec theta is essentially 1 over sine theta. What is sine theta? We are told that sine theta is what? 5 over 13. So if sine theta is 5 over 13, cosec will be what? Flip. So if I have 5 over 13, the answer becomes what? 13 over 5. The last one there says what? Cot. What is cot theta? 1 over tan theta. What is tan theta? Tan theta we got to be what? 5 over 12. So cot theta will be 1 over. Cot theta will be 1 over tan theta, or simply say flip tan theta. So tan theta, if tan theta is 5 over 12, then cot theta will be what? 12 over 5. So that settles this answer. So you see where trigonometric ratio marries Pythagoras theorem. This is just one of such iterations you're going to get where these two aspects relate together. We said you're going to see very soon how these two aspects will now connect to what is called trigonometric identities. By the time we come to identities, we would expect that your knowledge of this ratio and knowledge of ratios and Pythagoras theorem are very concrete. So when you marry these two aspects together to talk about the identities, it becomes a very smooth ride. Okay, I'll allow you to take a breath and then we'll continue. So when we talk about trigonometric ratios or special angles, what comes to our mind? And what makes these angles so special? These angles are special because we can obtain their values, we can obtain their ratios from two known standard triangles. So watch carefully. We said that when we're talking about trigonometric ratios, we talked about, when we started trigonometry, we talked about the right angle triangle. Now, watch something. We have two special types of triangles, and these two special types of triangles will generate situations that are very peculiar for us. Now, imagine a right angle triangle that is isosceles. We said that for an isosceles triangle, the base angles are equal. So don't mind the way I placed this triangle. This is essentially a right angle isosceles triangle. Right angle isosceles triangle, meaning that if I mark these 2 points as equal, it means this angle here must be equal to this angle here. Recall that we said that this angle is 90 degrees. So if this is 90 degrees, it will mean that this is what? 45 degrees. And this is what? 45 degrees. Because if I add these two, I'll get 90. I remove it from the sum of the angles of a, rather, I have this angle will be what? 180 minus 90, this 90. These two angles will be left to share 90 degrees. So this will be 45 and 45. Now that's one scenario. There is yet another scenario where you have an equilateral triangle. An equilateral triangle is such that all the sides are equal. So invariably, every angle here is what? 60 degrees. If the sum of the angles of a right angle, rather of a triangle is what? 180 degrees. If the sum of the angles of an equilateral triangle is 180, if the sum of the angles of an equilateral triangle is 180, it will mean that every angle will be what? 60 degrees. How? 180 divided by 3, and that will give you what? 60 degrees. So from our knowledge of construction and loci, if these angles are all equal, I can actually cut this. And if I do that cutting, what will happen is that this angle will be 90 degrees, this angle will be 90 degrees. This angle now will change to 30 on this part, and this will change to 30 on this part. So this will become 30 degrees, and this will become 30 degrees. So what we have will be two special types of triangles which will enable us to do what? Obtain, which enable us to obtain what is called special trigonometric ratios of our special angles. Now, for the purpose of study, we assume that all the sides of the equilateral triangle are 2. So if this is 2, this is 2, and this side is 2, and this angle is bisected, it means this side will be 1, and this side will be 1. So we introduce a letter H that we need to look for what this side will be. In like manner, if this side we introduce for the isosceles right angle isosceles triangle, we introduce 1 here and introduce 1 here. These two sides are equal. So how do we obtain this? I'll just call this, let me introduce the letter A. So I'm going to redraw this. What you're going to technically have is something like this. 1, 2, and I need to get this part. So from what we have studied so far, you will get that h squared plus 1 squared will be equal to what? 2 squared from our Pythagoras theorem. And then it means that h squared will be equal to, will be what? Plus 1 equal to 4. So what is h squared? 4 minus 1. Then what is h? H will now be the square root of what? 3. So where I have h, I will then replace this with what? The square root of 3. Now come here. Trying to solve for this one. Now, from our Pythagoras, we know that a will be a squared will be equal to 1 squared plus 1 squared. Looking at this right angle triangle. And it means that a squared will be equal to 1 plus 1. And a will be equal to the square root of what? 2. Because 1 plus 1 is 2. And then the square root will now be of a will now be the square root of 2. So where I have this, I will now change this to what? Root 2. So with this, the question now will be, what are the special angles? So the special angles are 0, 30, 45, 60, and finally 90. So these are the special angles we are going to have. So to further buttress what we're doing, we're going to draw something like a table here. We're going to draw something like a table there and try to fill in this 1, 2, 3, 4, 5. All right. So we're going to have sine. We're going to have cos. We're going to have tan. Let me stretch it. We're going to have cosec. We're going to have sec. And finally, we're going to have cot. This will be 0 in degrees. This will be 0. This will be 30. This will be 45. This will be 60. And this will be 90. Now, when I'm generating this table for students, I always start with what I call the obvious. I start with what I call the obvious. There are some that are just very obvious. So I like to do the obvious first. Now, to generate this table, I needed to look at what we have done here and here. Now, let me fix this properly. This will be what? 30. And this will be what? 60. 30 degrees, 60 degrees, right? So, now, I won't do 0. Because I'm going to explain to you something that will shock you now. Now, when we talk about sine, now, I need you to watch because sometimes when we try to explain this concept, when we try to explain 0, it's really very difficult for students to perceive what 0 looks like. Now, imagine you have a right angle triangle like this. Please, let's watch. This is a right angle triangle, is that not? Now, they say sine 0. Do you know what sine 0 means? It means that there is no what? There's no opposite. So imagine if sine 0 will be something like this. Whether 0 will be something like this. Imagine if it were possible. It means that at that measurement, at that point in time, the hypotenuse and the adjacent are the same value. So it means that you don't have a. So let me do a little deduction here. I guess you're through with this part. So let me do a little deduction here for you to see, because this is where the confusion is when it comes to this description. Now, for 0 degrees, the interpretation is that what? You have opposites. No, you don't have opposite, no opposite. Adjacent and what? Adjacent and hypotenuse are one. Represent just one. So they are unitary. Look at it. If we say sine 0, now watch this. So 0, 60. I saying it. Remember, I said opposite has to do with what you are saying. So if there's no angle, if it's 0, which means I'm not saying opposite. And allow your imagination work. It means that if this condition would exist, the opposite, the adjacent, and the hypotenuse are the same value. Because look at it. What you're opening is the hypotenuse. I seen it. You're opening the hypotenuse. Are you looking at it? You're opening the hypotenuse. So it is your opening of the hypotenuse that brings about the angle here. So this is adjacent, this is opposite. So when there's no opposite, it means that sine is what? Opposite. When there's no opposite, it means opposite is 0. And as such, sine 0 will be what? 0 over 1. So in that setup, this will be what? 0. Because sine 0 will mean what? No opposite over the hypotenuse. Because we've established that for 0 degrees, we have no opposites. But adjacent and hypotenuse are what? 1. So those are the ones that are present. And those values are equal. Settled. Now, we come to cos 0. What will cos 0 now be? Remember that we have said that adjacent and hypotenuse are present. What is cosine? Cosine is adjacent over hypotenuse. So it means that this one will be what? 1. Have you seen why cos 0 is 1 now? Because you have adjacent and the hypotenuse present. Now, what about tan? Tan is what? Opposite over adjacent. Tan, maybe I should just help with this S. Sine theta is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tan theta is equal to opposite over adjacent. I see that. So what that invariably means is that I would have said that adjacent is 1, hypotenuse is 1. So this will be what? 1. Now, for tan theta, you have no opposite. That's 0 over adjacent, which is 1. 0 over 1 is what? 0. Now, for this one, what will cosec theta be? Cosec theta will be what? 1 over this, which will be infinity. 1 over 0 is equal to infinity. Now, what will sec theta be? To still be 1. 1 over 1 is what? 1. What will cot theta be? Cot theta is what? 1 over 0. And that will be what? Infinity also. 1 over 0 is also what? Infinity. Just for you to remember that. Now we come to 30. Now look at 30 here. If you look at this angle 30, what is the opposite? It is 1. So this is opposite for 30 degrees. Opposite is equal to 1. Adjacent is equal to √3. And what? Hypotenuse is equal to 2. So if they say sine 30 degrees to be what? 1 over √3. 1 over √3. So what is cos 30 degrees to be what? Adjacent over what? Hypotenuse. That will be what? Oh, sorry, that's in 1. Sorry, that will be 2. Sorry about that. That will be 2 over √3. Opposites. Oh, sorry about that too. Like I made another mistake. It will be 1 over 2. Opposite 1 over the hypotenuse 2. Now what will cos theta be? Cos 30 rather to be √3 over 2. What would tan theta be? It will be 1 over root 3. Now, these remaining ones, you flip them. What would cosec theta be? To simply be what? To turn this. What would sec theta be? To simply be to flip this. That would be what? 2 over root 3. What would tan theta be? To simply be what? Root 3. Are we seeing that? All right. Now we'll go to 45. Where do we get 45 here? Cos 45 degrees will simply be what? 1 over root 2. Or rather sine 45 degrees will be what? 1 opposite over hypotenuse. So that will be 1 over root 2. Cos 45 degrees will be what? Adjacent over hypotenuse. Now, tan 45 degrees will be what? Opposite over adjacent. 1 over 1 is 1. So what will cosec be? Flip this one. What will sec be? Flip this one. And what will cot be? Flip this one. Flipping of 1 will still give you 1. Now, what about sine 60 degrees? Sine 60 degrees will be from this one. Look at it. Root 3 over 2. What will cos 60 degrees be? It will be what? Adjacent over hypotenuse. Now, what will tan 45 degrees, tan 60 degrees be? Root 3. So, cosec means flip this one. Sec means flip this one. And cot means what? Flip this one. Right? So, next one will now be, let's write this one well. This will be 1 over root 3. And what's the next one? We come to sine 90 degrees. Now, when we come to 90 degrees, look at what's happening. Look at it. Now, this is where your imagination needs to work. As you begin to open your opposite, now hear this. In this arrangement, opposite, when you're considering 0 and 90 degrees, only one of opposite or adjacent can exist. Notice that the hypotenuse will always exist. I'll come again. Because it took me a long time to crack this. It took me a long time to crack this because when I remember when my teachers just mentioned those things, I was wondering, what's happening? But I had to develop this method. Now, when you consider 0 degrees, you're not seeing opposite. So, of the 3 sides, 2 must exist per time. So, when you talk of 0 degrees, the only 2 sides existing will be what? The hypotenuse and the adjacent. When we now talk of 90 degrees, see what's happening? As I begin to open up the opposite, the adjacent begins to disappear. That's what you must understand. So once you get to a straight line like this, you're going to have at 90 degrees that the opposites and the hypotenuse will be the only things existing. The adjacent will not exist. So if you have that understanding, it means that here at 90 degrees, you're going to have that there will be no adjacent. No adjacent. So opposite and hypotenuse are 1. So at 90 degrees, the opposite and the hypotenuse are the only 2 sides that will exist, technically. Some of this, you see, maths is interesting when you see a lot of these things you think I'm even giving to you. You will discover better than myself. Some of these things I didn't learn them in a classroom. With time, I started seeing some of these things on my own, and that's where learning starts. Not only the students learn, the teachers also learn. I've learned a lot from teaching students. I'm what I am today because I've spent time teaching students. Now, so for 90 degrees, we don't have adjacent. So this will be 1. Because Sine is what? Opposite of hypotenuse. And I've told you that opposite and hypotenuse exist. Now, what about cos theta? Remember that under cos 90, you don't have adjacent. What is cosine? Adjacent over what? Hypotenuse. That's 0 over 1. So this will be 0. Now, what about tan? Tan, we've already said that you don't have what? Adjacent. So for tan, 90 degrees is going to be what? 1 over 0. And that is what? Infinity. So you flip this. 1 over 1 will still be 1. And are we together? 1 over 1 will still be 1. Also, rather cosec. Cosec will be what? 1. We flip this. I'm going to get infinity here. I flip infinity, I'm going to get what? 0. Now, 1 over, look at this. 1 over 0 is equal to infinity. So 1 over infinity will be equal to 0. Because 1 over infinity will mean 1 divided by 1 over 0, which will be like saying 1 times 0 over 1. That will be what? 0. So, this is what we have as the special, because the idea behind having this is that, one, when you're giving problems like this, you're not expected to use four-figure table. 2, this topic directly ties up with the concept of swords, because sometime later, if we rationalize, we can actually get some things here. That's 2. 3, we expect you to memorize this and also be able to state some relationship between these. We're not going to do that today, but in my next class, I'm going to show you something interesting. Conclusions we can draw from this table. There are conclusions we can draw from the interaction of this on this table. So I'm going to pause the class for now. And in my next class, I will expect us to go into the quadrant system and perhaps use that as a basis to begin to solve problems. We'll solve problems in the next class and also try to look at the quadrant system.